All right, so let's look at this example here. So it says that you need to determine the density of an unknown liquid. You notice that a block floats in the liquid with 4.6 centimeters of the side of the block submerged. Whoops, that was supposed to be the highlighter tool. When the block is placed in water, it also floats, but with 5.8 centimeters submerged. And we want to find the density of the unknown liquid. All right, well, I don't know about you, but I want to draw some sketches here first. All right, so let's first focus on the unknown liquid. All right, so I'm just going to draw kind of a line here representing the surface boundary between the unknown liquid below here and the atmosphere above. And we've got some sort of, whoops, I want some sort of cube here. So I'm drawing a cube, and that is partially underwater. And the height here underwater, we're told in the problem, we'll call this height unknown. Whoops. Height unknown. And that's 4.6 centimeters, which, yes, we will be converting to meters. And then sketching, we also have the situation with the water, which looks similar, except for our block is submerged. This is the same block. It might look larger, but your eyes are deceiving you. Same block. And this height here, which I'm not writing the letter I, I'm trying to draw a little bar. We'll call this height for the water is 5.8 centimeters. Now you might think, all right, we're done drawing diagrams. Well, hopefully you weren't thinking that, because we should draw some free body diagrams. So, for our block in the unknown fluid, we've got the weight of the block acting downward. And then we have, let's see, buoyant force acting upward. And the buoyant force, since the block is in equilibrium, is equal to the weight. Great. Block in water. We've got force of gravity downward, and nothing has changed about the block's weight. So therefore, we have buoyant force upward. And what's particularly interesting here is since the weight of the blocks are both the same, then since these blocks are in equilibrium, therefore the buoyant forces acting on in each situation are the same. So the buoyant force for the unknown liquid is equal to the buoyant force for the water. This is an F. There we go. All right, so let's apply the formula for buoyant force. So for the unknown liquid, we have the density of the unknown liquid, the volume displaced of the unknown liquid, times gravity, acceleration due to gravity, excuse me. And similarly for the water. All right, so what's nice here is we don't have to worry about the gravitational accelerations. Now, looking at what we know, or what we're trying to figure out, right? Well, density of water is a known quantity, right? Density of water, wow, should not be writing in that angle with this broken pen. Density of water is 10 cubed, kilograms per meter cubed. All right, so looking at the information we're given height, all right, but in the formula we've got volume. Well, luckily those were late, right, because we've got the area of these blocks below times the height of the submerged fluid is going to be the volume of the fluid displaced. So we can just write volume as area times height. So we have density of the unknown fluid times we'll call it the cross-sectional area of the block, times the height of the unknown fluid is equal to the similar expression but for water. And these areas are the same because we're dealing with the same shaped block. All right, so then therefore we have an expression for the density of the unknown fluid. That's going to be the density of water times the height of the water divided by the height of known. Ooh, interesting. What do I just find interesting here? Well, what I find interesting is earlier I had said, hey, we're going to convert to meters. Of course, why wouldn't we? We're dealing with physics problems. We always convert to SI units. Well, we're dealing with height divided by height. The units there are going to cancel out, so it doesn't matter if we convert or not. So, convert, don't convert, up to you. Rounding to 2 sig figs, we end up with 1,300 kilogram per meter cubed. Now, so we basically have identified the density of the unknown liquid. That's great. So if we're curious to see what this liquid actually was, or this fluid, we could look this up in a density table, and we see this is actually the density of glycerin. All right, so the unknown fluid is glycerin.